Hi everyone, welcome to another NERV event. Can I maybe just get a comment or so to see if everyone can hear and see me? I am having some connectivity issues, so just to be sure that the stream is working. Maybe just perfect. Okay, everyone's saying it's good. Okay, welcome. So as always, we are the Neural Engineering Research Venture, and our aim is to bring neuroscience to life in Africa and around the world. And Siobhan and I will be your hosts for the evening, and Jarvi is usually lurking in the comments, so you guys can look out for him there. Then today we have a special event. We are celebrating Mole Day. So in commemoration of Mole Day this Friday, the 23rd of October, we celebrate the significance of Avogadro's constant. Avogadro's constant, approximately 6.02 times 10 to the power of 23, is the basic measuring unit in chemistry and was discovered by the 19th century scientist Amedeo Avogadro. Mole Day aims to celebrate and foster an interest in chemistry and is rightly celebrated from 6:02 a.m. to 6:02 p.m. on 10/23. So with that, we also have a couple of announcements. First announcement is NeuroMatch. So NeuroMatch is hosting another conference. This time around, it will be a super conference. So this means that it is not just limited to computational neuroscience, but the entire spectrum: computational, developmental, social, clinical, cellular and molecular, motor, sensory, education, ethics, animal, and human. They've designed an awesome algorithm to group talks based on fields of interest. And this is to make it easier to choose which talks to attend. And this conference will run from the 26th to the 31st of October, and there will be keynote and poster sessions. So definitely do check this out. And I think Siobhan will also be sharing the links to all of these announcements in the comments, so you can follow those there as well. Then immediately after NeuroMatch, Black in Neuro is hosting a conference. This totals almost 2 weeks of great neuroscience events. And the Black in Neuro conference will run from the 31st of October through the 4th of November. Then, if you are a grad student or postdoc interested in presenting your work to a large neuroscience audience, we are introducing Neuro Launchpad here as well. And this is a virtual seminar series that's very cool, and it's designed to give exposure to trainees. So the seminars have already started and will continue until December with 2 20-minute talks a week, and they are already accepting submissions as well. Then also save the date for the Simons Emery workshop on neural dynamics. This will take place on the 4th of December on YouTube. The workshop will center around the question, what could neural dynamics have to say about neural computation, and do we know how to listen? Okay, so that's it for our announcements. Then a couple of house rules. Please remember to use respectful and inclusive language, as we have a very wide variety of attendees in our audience. Then also remember to ask a question. Throughout the talk, post your questions in the Ask a Question section, and then also vote for your favorite questions. Then after the presentation, we will invite you on screen to ask your questions live. If you don't want to ask your questions live, and this is very important, please remember to add "Please ask me" at the end. And then the way the system works is the most popular questions are more likely to be asked first. And also, if you don't have a mic, also don't worry about it. Don't let it deter you from asking questions. We will still ask on your behalf if you just add "Please ask." Then if your connection is slow, try to refresh your browser. Or alternatively, you can select the compatibility mode from the audiovisual help button at the bottom of your screen. But if your connection fails completely, the talk will be available to stream after the event. With this, I will now hand over to Siobhan, who will be introducing our speaker for today.
Thanks, Julianne. Hi, everyone. I'm very excited to introduce our speaker, Dr. Ndivhuwo Makondo, who will be giving his talk tonight on logical neural networks. Ndivhuwo is a research scientist in artificial intelligence working on integrating symbolic AI and neural networks into neurosymbolic AI techniques, as well as applying reinforcement learning to healthcare problems. Previously a robotics researcher at the CSIR in the mobile intelligence and autonomous systems, he was working on developing techniques for robot vision and manipulation. Prior to that, Ndivhuwo completed his PhD in machine learning and robotics at the Tokyo Institute of Technology in Tokyo, Japan, and his MSc and BSc in electrical engineering at the University of Cape Town. Thank you very much for joining us, and we look forward to your talk.
Yeah, thank you for the invitation. I'll start sharing my screen now. Can you guys see my screen? All right. Okay. All right. Thanks for everyone for joining today's talk. I see we have a big audience today. So I will be talking about logical neural networks, which is a framework for combining symbolic AI and neural networks that we working on at IBM Research. So this is a collaboration among several IBM research labs, including our lab in South Africa, in the US, and some labs in India. So I am going to try and give a brief conceptual introduction to logical neural networks, because there's actually a lot in it. I am going to assume some basic understanding of symbolic AI, that is logic and inference. I'm also going to assume some basic understanding of neural networks. All right, so this is the overview of my talk. So I'll start with a brief description of what neurosymbolic AI is, which is the umbrella in which we're developing logical neural networks. Then I'll spend a substantial amount of time describing conceptually what logical neural networks are, and then following the inference process, the learning process, and some discussion on and some future work. So this is based on, so we do have two publications on arXiv, which are under review at two conferences. So if you want more details about this work, please go have a look at these two papers. The first one at the top is the theoretical proof of soundness and completeness of real-valued logics. And what I'll be talking about is an instantiation of one of the real-valued logics combining with neural networks, which is the paper at the bottom. So what is neurosymbolic AI? So here the goal is to try and bridge deep learning and symbolic logic so that we can circumvent some of the limitations of both fields while combining their strengths. On the left, we have neural networks or learning in general that is able to learn from unstructured data. And this has been used in various domains, for example, perception, for feature extractions, object extraction, and semantic parsing. And recently, neural networks have been the dominant paradigms in this domain. On the right, we have symbolic AI, where here the idea is to encode the natural world in some formalized knowledge. So typically you assume some logical representation, propositional logic being the simplest form. You say first order logic and some higher order logic. The idea here is...
Dr. Makondo, sorry, I just want to say it seems there's a problem with the presentation
Really?
in that not changing the slide. So I'm just going to ask you to maybe reshare your screen to see if that works. Sorry, apologies for the interruption.
Okay. Is that better?
Okay, just maybe click to the next one. Okay, no, it's still not. Okay, yeah, it seems like it's working now. Yeah, I'm not sure entirely because there's a small change on the screen happening. Just click forward a couple of slides. Okay, yes, okay. Everyone says it's working now. Perfect.
Okay, all right.
Thank you. Sorry.
All right. Yeah, so I was still describing a symbolic logic where the goal is to build a knowledge base represented in some logical language, propositional logic being the simplest form, and also having first order logic and higher order logics. And the knowledge base contains of facts and also symbolic rules or background knowledge. And the idea is to build logic programs from this knowledge base of facts and rules such that it can perform some reasoning and answer some queries. And the idea of neurosymbolic AI is to combine these two paradigms into a single framework that can do logical inference and also learn from data. Then what really is a logical neural network? So this is basically a neural net that has a one-to-one correspondence with a system of logical formulae. An inference in this system is equivalent to logical inference. Given a simple example here, can you guys see my cursor? I'm just going to assume you guys can see my cursor. So given a simple model, a logical model in propositional logic, where we would like to predict whether we're observing a cat in our environment, we actually have simple propositions such as whiskers, tail, laser point, and chases, combined with logical connectives such as the conjunction and the implication. And this is basically a rule that describes that if we're observing whiskers and tail and something that given a laser, it chases it, that implies it's a cat. And we can also have a simple model that models what a pet is. This is a very simplified example since there are so many animals that we can consider as cats and as pets. In this example, we have cat or dog is a pet. A neural network, a logical neural network is basically a syntax tree mapping into a graphical structure where you have propositions as input combined by logical connectives. The significance here is if this logical connect or classical logical connectives are replaced by differentiable of activation functions, you can actually use back propagations or gradient-based learning to update the weights of these functions from data. Assuming or taking advantage of the structure provided by symbolic AI, we can actually keep these neural networks interpretable as opposed to current neural networks that are actually black boxes. And this also allows us to incorporate domain knowledge. For example, one actually has to design a rule that describes what a cat is. And we can actually use that domain knowledge to design the structure of the neural network. The LLM also supports compound first order logic formulae and also adheres to open world assumptions, as I will show in the next few slides. So more concretely, on the left, we have neural networks that tolerate noisy and unprocessed data. They require a little...
Sorry for interrupting again. It seems it's still the same problem. So it's a small part of the screen that changes, but the main slide remains large. So we're thinking maybe we should try and minimize your presentation so it's not full screen to see if that maybe works.
Okay, I'm not sure what's causing that. Is it my network connection?
I'm not sure. It shouldn't be the network connection. I don't know if it's maybe just a glitch with the iOS interface with crowdcards. I don't know. But we can try and sort it out that way if you maybe minimize. Otherwise, if you want to send your slides to me, I can try and share them. But that might cause a bit of a delay.
Okay. Well, it's actually not full screen, but I don't know if you just want me to make it a bit smaller.
It's very strange because now the screen I can see that you change it to is also just a small square. So maybe if you share your screen again and you click on the full presentation. So I'm gonna ask you to share it again, your screen.
Okay.
I'm so sorry for this. We've not had this problem before. Apologies, everyone. Thanks for bearing with us. Okay, so if you run through your slide chain now, no, it's still doing that. If you close the presentation window completely, and you just sort of click through the slides. Oh no, this is very strange. It's doing the same thing. It's probably on your end, it's probably just looking like the presentation, but it seems for everyone there's a small square on the presentation that keeps changing while everything else around it is frozen.
I'm not sure what's really causing that.
It's very strange. Siobhan is suggesting if you unplug the second screen and run everything from your main computer.
Okay. Can you see my slides?
No, not
Am
yet.
am I no longer sharing?
Yeah, I think you'll have to reshare now. Thanks for the suggestion in the comments, Cameron. Yeah, we're trying to see if that works now. Okay. Seems we lost our speaker. I'll just. Oh, he's reconnecting now. Okay, let's just give him a moment. Otherwise, I will re-invite him. Okay, let's see if this works. Siobhan, I'm just inviting you as well so we can coordinate a solution. Okay, never mind. Okay, so our speaker's been re-invited. Just waiting for him to connect. Apologies, everyone. I know this is not fun. Okay, our speaker is connecting again. Okay, hi.
Am I back?
Welcome back, yes. Okay, so you can try sharing your screen now. Okay. Perfect. Yes, now I see your PowerPoint. And your slides. Yes, now they're working. Perfect. Perfect.
Okay.
Awesome. Yeah. Okay, great. Sorry again for the interruption.
All right. Sorry about that.
Still time lucky.
Okay. Let me try to remember where I was. I think I was on this slide describing the properties of neurosymbolic AI. So the hope is that by combining neural networks and symbolic AI, we can obtain learning-based systems that are trusted and explainable, that have some sort of causal relationship, mainly because they build on top of rules, if then rule statements that are designed by humans. And when replacing the neurons with logical connectives, we can, well, by implementing differentiable functions for logical connectives, we can obtain a system that is end-to-end differentiable. There is actually a lot of work on trusted AI and explainable AI that is not using symbolic AI. But since these symbolic AI systems have shown to be interpretable and generalizable, a part of us at IBM with thought this would be a better way of looking at more interpretable and explainable learning systems. So this is definitely not the only way going forward. Actually, there has been a debate between Yoshua Bengio and Gary Marcus on whether we need to be taking ideas from symbolic AI and combining with neural networks. So it is an ongoing debate. Hopefully, in due time, we'll be able to show that there's actually value in combining neural networks and symbolic AI systems. So since logical neural networks are actually combining symbolic AI system neural networks, we actually take a representation of a logic program and represent it in a tree structure and replace logical connectives with neurons that are actually constrained to behave logically. In symbolic AI, there are actually several logical representations. In first order logic, it attempts to model the world in terms of objects and properties of these objects and relations. And the relations are modeled with predicates. And you can actually create a composition of these predicates with logical connectives in order to create more complex logical sentences, which we call logical formulas. You also have quantifiers that allow you to make general statements about the world and also specific statements about specific objects and relations. So this is represented in a syntax tree, and we borrow ideas from neural networks where instead of having logical connectives, we have logic neurons. So these are neurons constrained to behave logically. And you also take ideas from neural networks of having weighted inputs. We do also propose new concepts such as truth value bounds. Instead of having a single true or false, as in classical logic, we have bounds on the truth values. So I'll discuss in the next few slides. So in classical logic, you either have a statement is either true or false. But we know the world doesn't behave that way. That's why you have probability theory that talks about the probability of something being true or false. Also, with neural networks, when you're looking at classification tasks, you have probabilities of an input or an image belonging to some class. With the logical neural network, we propose a new idea of tracking truth value bounds. So instead of keeping track of a single number, we keep track of two numbers, one representing the lower bound on the truth value and the other representing the upper bound on the truth value. When the lower bound is false and the truth value is false, we regard this as an unknown statement. So we don't know anything about it. We don't have enough information. When both upper and lower bounds are false, then we know for sure with the degree of truth is actually false, and vice versa for the true statements. We also have the fourth state, which is actually a contradiction, which is when the upper bound and lower bound cross. So the upper bound is lower than the lower bound. And an important property of tracking these lower and upper bounds is that we're able to make the open world assumption. In classical logic, typically the closed world assumption is made, which states that anything that is stated is assumed to be true, and anything that's not stated is assumed to be false. But with true value bounds, we're able to say that anything that's not stated is assumed to be unknown. So here we do have on the right, the top right, we have a simple propositional logic program where you have propositions E, D, and C, and at the bottom you can see a logical neural network representation of that. In logical neural networks, they actually add weights to the connections, just as in typical neural networks. And using this statement as an example, you actually have, instead of having classical conjunctions, you have parameterized connectives that actually have weights and bias that can be learned from data. And these weights are actually modeling the influence of each proposition on the output of the entire logical statement. So before moving forward, I'd like to briefly describe some basic concepts in logical inference or symbolic AI. Here I'll be using propositional logic because it's actually simpler to understand the concept using propositional logic, but the LNN is not limited to this. We're going to also use first order logic. So in propositional logic, you have the syntax, which is basically consists of propositional symbols. Here it's a proposition P or Q. You have logical connectives, you have your AND, or, not, implies, and by conditional gates. And the semantics are actually described using truth tables. On the right, we have the truth table of the implication and also the conjunction. The conjunction is basically only true if both propositions are true and false otherwise. You can interpret this as a function that maps propositions into the range between 0 and 1, but in classical logic, it's actually a set of 0 and 1, so it can either be 0 or 1. The conjunction is only true when both propositions are true. So it turns out that the very first attempt to model neurons artificially was actually intended to model logic gates. And this was obtained by actually designing an activation function that maps inputs to the output with weights that are ones. And this actually, the only parameter here is the beta, or sorry, the theta, the threshold. For example, for a conjunction with two inputs, if you set the threshold to 2, this actually models the truth table of the conjunction. So it's only true if both propositions are 1, which is greater or equals to 2. And this is actually, the activation function is actually modeled as a step function. But there was no learning involved in the first artificial neuron model, but evaluation actually corresponded to logical inference. Then work began to actually generalize this model into a neuron that we all know now, where instead of weights being 1, this can be learned, and this actually expressed the importance or influence of inputs on the output. When you have equal weights, this actually behaves like an unweighted case, and if any of the weights are 0, actually removes the influence of the input on the output. And this results in a continuous function of the weights. So in a logical neural network, we're actually looking for activation functions that can be constrained to behave logically. And the choice of that activation function actually determines whether we can preserve some logical tautologies. And this is because this is assumed in knowledge-based designs. So since we want to use domain knowledge, typically represented in some logical representation, we like to preserve tautology so that any transformations to the logic remains logically sound. And the idea is to replace these connectives with continuous functions so that we can operate within the fuzzy region instead of 0 and 1. So we want continuous outputs, but still behaving logically. And this actually eases the interpretation of the entire model. Instead of just having neurons that we don't really understand what they're computing, we have each neuron representing a logical connective, whether it's a conjunction or disjunction. So that actually allows us to be able to interpret the model, at least more than what we'll be able to do with the standard neural networks today. So it turns out that actually a clamped ReLU function actually satisfy these properties. An important concept that we also introduce is the idea of alpha, which is basically the threshold of truth. This basically means that the output of a logical gate, if it's above alpha, we consider that to be true. If it's below 1 minus alpha, we consider that to be false. And the main reason to have this alpha value is so that we're able to have gradients in order to learn with classical logic. Otherwise, if alpha is 1, we only have gradients when we're in the fuzzy region, but 0 gradients when we're in the classical region. And in order to learn these weights from data, instead of using the standard gradient-based optimization using neural networks, we require to put some constraints on the parameters of the activation function. The first one being that all weights must be greater or equals to 0, and also the beta must be greater or equals to 0. And using the conjunction as an example, if any of the inputs is false, then the conjunction must be false, modeling the actual truth table using classical logic. And if all the inputs are true, or if the sum of the weights is greater than the threshold, then the conjunction is true. So when you do backpropagation, instead of just naively updating your parameters, we actually use constraint optimization to ensure that the weights are updated in a way that the neuron behaves logically. If initially it was a conjunction, it must stay a conjunction. So what are the inputs and outputs of the system? So the inputs is actually a knowledge graph or data. So I could have a knowledge graph where I have facts about whether we observe whiskers or tail in the environment, and I've also handcrafted rules that actually predict whether something's a cat or not. In contrast to standard neural networks where you have an input layer and an output layer, here any node can actually be an input depending on what you're observing and what you want to know. For example, the implication can act as an output, as a query. When I've observed whiskers, tails, laser, and chases, so I can actually perform inference to deduce that I'm actually observing a cat in my environment. Or I can have an observation that there's a cat, but I don't know if I'm seeing whiskers or tail, or any one of them. You can actually use rules of inference to deduce that given that I'm seeing a cat, then I must also be seeing whiskers and tails. So I talked about using truth tables to compute the output of logical connectives given the propositions as input. But you can actually have more complex statements, and it can be computationally intensive to always rely on the truth table to compute truth values. So there are actually rules of inference shown on the right that actually model what the computation of logic gates. For example, just looking at the first statement, this basically says that if the proposition P is true, and we assuming the rule P implies Q is true, then I can deduce that Q is true. And we have several such inference rules for different logical connectors, such as conjunction and disjunctions. So inference in logical neural networks is designed to follow logical inference in classical logic when working with classical inputs, but also behaves intuitively when working with continuous values. By intuitively, I mean if the inputs of the conjunction are higher but not actually true, then the output of the conjunction must also be higher, and vice versa. And also in contrast to standard neural networks, rather than having computations in one direction, where in the upward direction in the logical neural network, we're actually interested in computing the truth value of the output given the truth value of all the inputs. We can also do inference in the downward direction, where if we given the truth value of the output, we can compute the truth value of each of the inputs, where we actually loop through all the inputs and fix truth values for. So we isolate one input and compute its truth value, given the truth value of the output and the truth value of the other children, and loop through all the children, repeating the same process. And actually performing these computations correspond to rules of inference that I showed before, depending on what gate we're dealing with. For example, in the conjunction, downward inference says if I know the truth value of the output, which is the output, then if I know it to be true, then I can deduce that its output, all of its inputs must also be true. So how do we do inference in an entire LNN graph? So the first thing is to initialize neurons with observed truth values. So for any propositions for which I know the truth values, then I use those values as initialization. Any proposition for which I don't know the truth value, I just keep it as unknown. And the algorithm proceeds as follows. We compute the upward pass on the entire graph and compute truth values of the outputs. Then we computed the downward pass, computing truth values of the inputs given the outputs. Then aggregate the truth values given that have been computed with truth values that we began with. And predictions is basically inspecting any neuron that we're interested in. And this process as follows. The upward direction is basically computes the truth value of the output given the truth values of all the inputs. So it's basically looping through all the nodes in the graph and compute inference in the upward direction. And in the downward direction, we actually compute even the ones we computed in the previous round. We can then compute the truth values of the inputs one at a time in a depth-first search manner. And this continues until all the neurons have been computed, their truth values. And the last step is actually aggregate all the outputs that we've got from the computations with the initial values we had in the beginning. This can also be extended to first order logic, where in addition to having neurons for logical connectives, we also have quantifiers. So the neurons actually have what we call groundings. So grounding is basically a set of constants that we're dealing with and associated truth value bounds. And we actually learn the parameters of the logical connectives, and these actually implement inference rules. In quantifiers, we also have groundings and bounds, but there's no learning that occurs at these nodes. We also have a special node, which is the negation, which basically passes through information from children to parents on the negated truth value bounds. And it can also pass through information from the parent to the child, and that's also the negated bounds. We also have predicates that describe properties for unary predicates and relations between objects for n-ary predicates. And then also have terms such as constants, variables, and functions. So how do you actually train the logical neural networks? So we actually use gradient-based constraint optimization, as I've already explained. And all our operations are actually continuous because we're replacing logical connectives with continuous functions that still behave logically. And if you use the smooth versions of these functions, they actually become differentiable. So we're able to use backpropagation to update the parameters. The only operations that are not differentiable are the quantifiers. And there's no learning in the quantifiers. So we do have several training paradigms. The first one is you can actually inject a new node or a new logical statement that acts as a logical target. So, for example, in the cats and dogs example I shown before, I can actually inject a new statement, that actually add another classification output. We can also use logical consistency to train. So this actually allows it to learn in an unsupervised manner. In this case, we don't have any output of interest. All we're interested in is avoiding any contradictions in the knowledge base. In classical logic, if you have contradictions, that actually renders your system invalid and you're not able to use it. But by using continuous functions for logical connectives, we're actually able to learn to reduce the contradictions by adjusting weights on these connectives. And we also have a way of learning for specific tasks. This is if you have specific outputs you're interested in. And so you can actually compute truth values for those outputs and compare them against ground truth. And you can use that to compute the loss and use backpropagation to update the weights. So this is the loss function that is actually used, or it's a very general loss function that can be used, but you can also add other terms depending on your task. So the first component is basically your regularization terms in standard neural networks. You have the L1 norm and the L2 norm. On the right, we have the contradiction loss. So this basically says every time the lower bound is higher than the upper bound, you want to try to minimize that across all the nodes. So this basically tries to adjust the weights such that you minimize contradictions in the entire network. And with those two components, you can actually learn in an unsupervised manner if you don't have any ground truth examples available. And this actually learns to adjust weights so that you refine your rules based on any contradiction information that exists in your knowledge base. But if there aren't any contradictions, then that will basically do nothing. And if you have any examples available for a specific task, then you can add what we call the task focus loss component. That can be like the mean square error, for example, which basically learns to minimize the discrepancies between your predictions on the lower bound and also the upper bound on the ground truth. I don't know how I'm doing in time. Am I still doing fine? Since I only have one screen, I cannot see what's been typed in the chat.
Hi. Yes, you're still good for time.
Okay. So I'm going to give a toy example that is typically used in neurosymbolic research, just to show some of the problems that the logical neural network is able to solve currently. So this is called the Smokers and Friends benchmark. So you have a knowledge base of facts that has entities A to H. In this case, these are people identified with letters from A to H. So A is a specific person, B is a specific person, all the way to H. And you have the S predicate, which stands for smoking. And you have the F predicate, which stands for friends. And also the C predicate, which stands for cancer. So the facts given here in first order logic is basically saying that person A smokes, person E smokes, and so on and so forth. And then also states that person B doesn't smoke, and person C doesn't smoke, and so on and so forth. This binary predicate is basically representing the fact that A and B are friends, A and C are friends, and so on and so forth. And then also has facts about which pair of people are not friends. Then it also has facts about people that have cancer and those that don't have cancer. On the right, you also have a knowledge base here in the domain of people from I to N. At the bottom, you have rules that have been handcrafted based on what the engineer or the user believes governs the dynamics. For example, you have a rule that says for all people, no one can be their own friends. You have the second rule that says for all people, if person X smokes and is friends with person Y, then person Y must smoke. You also have for all people, if one smokes, then they also have cancer. One thing to note is that these rules do not always apply in all cases. And so there are cases where someone smokes and also has cancer, but there are also cases when one smokes and they don't have cancer. So the goal here is to learn weights of the connectives based on facts in the knowledge base, such that these rules apply to the domain given in the knowledge base. So the idea is to compute weights such that when we compute the truth of the rule, it's not either 1 or 0. It can be 0.5 or 0.6. In the case of the LNN, it can be, we actually have truth value bounds. It can be between 0.4 and 0.6, which basically means we're very sure that 40% of the people that smoke have cancer, but we're sure that the number is above 40%, and we show that it's below 70%, but we fuzzy about where it is between 40 and 70. So we basically representing the background knowledge in a neural network structure using logical neural networks, and inputting the facts in the knowledge base and performing upward and downward inference, and actually learning on the actual observations that we see. We can learn to adjust the weight of the rules such that these rules apply to the facts provided. So this is a useful feature where so one of the biggest challenges of classical systems is that since they work with either true or false values, the rules that engineers handcraft must be perfect. But it's actually very difficult to come up with perfect rules. So the LNN allows you to start with noisy rules that can be adjusted based on observations. And this actually leads to more interpretable rules than if you were just using a standard neural network. So I will try to summarize by trying to look at the LNN from different perspectives. If you come from the neural network side, so neural network, an LNN is actually a feed-forward recurrent neural net with neurons arranged to match a system of logical formulae. And the weights are constrained to ensure classical logical behavior when the inputs are actually logical. And you actually have weights that share parameters depending on what propositions or effects are at play. But they are different from neural networks because they yield output in terms of bound pairs, so the lower and upper bound, that allows us to model things we don't know about. Or you can look at this as it outputs actually two values, either bounds, lower or upper bound. From theorem proving or from classical logic, so the LNN is actually similar to this because it actually computations on the network actually apply rules associated with each connective. So we're able to retain the interpretability of classical systems. At the moment, we're only looking at truth values at sub-formulas rather than any new formulas, which you typically need if you're trying to do theorem proving for proving math theorems. They differ from classical logic or theorem provers because we work with continuous values instead of either 0, 1, and also the connectors have weights. From the Bayesian network point of view, LNNs is actually similar to Bayesian networks because the edges between the nodes establish the positive and negative correlations between truth values. And any node can be input and output depending on what observations you have and what you're interested in. The LNN are different from Bayesian networks because the graph is actually more structural. It's more structured in general. Truth values at the moment do not have probability interpretations, but there's a team of researchers working at bridging the gap between LNNs and probability theory. And LNN, being a recurrent neural network, actually doesn't involve the costly normalization required when working with Bayesian networks. So in principle or theoretical, it should be more computationally efficient than using Bayesian networks. So next I'll talk about some future work. So currently we've only applied LNN on simple toy problems. So one of the future works is to use GPU acceleration in parallel computations. So the moment everything is running in a CPU in a sequential manner. And we also need to do some heavy experimentation on more large-scale data or benchmarks so that we can compete with neural-based systems while being more efficient and also more interpretable than neural-based systems. We are working on applying this the LNNs as in different applications. The first one as a real-valued reasoning component of a knowledge-based question answering system. We're also applying it to inductive logic programming, which basically the problem setting is that you don't have any rules to start with. All you have is facts, and you like to induce rules from these facts. And we like to induce interpretable rules from the facts that actually explain the facts. And there's also a team of researchers looking at applying logical neural networks in reinforcement learning so that you can have interpretable and explainable and simple, efficient RL policies rather than the neural-based policies that we have currently that actually simple, inefficient, and do not generalize well to novel users. And yeah, that's it. I will start taking any questions.
Perfect. Thank you so much, Dr. Makondo. It was a very interesting talk. So for everyone, please check out our poll or vote in our poll. And then I will give everyone a couple of minutes to get in your last questions before we start with the Q&A. And in the meantime, I will just bring Siobhan online so long. And again, apologies to our speaker and our audience for the technical difficulties at the start.
Do I need to still be sharing my screen or?
No, you can stop sharing. It's fine. Then we can make our feeds large on the screen. Okay, perfect. Welcome back, Siobhan.
Thank you so much, and thank you for the great talk, Dr. Makondo. That was very interesting. We have a few questions tonight, so I'm just going to jump right in. The first question is from Hope, who is asking about the possible applications of LNNs and how much difference they would bring about compared to existing neural networks.
Okay, so basically you can apply LNNs, well, in principle, to any application where you currently apply standard neural networks. The difference currently is that the input to the neural networks are actually propositions or facts represented in a logical formulation. So in natural language processing, this means that you have to do semantic parsing to go from natural language text to a logical representation. Then you can apply LNNs to do reasoning. And the advantage is that this can you can have more interpretable models. You can also incorporate domain knowledge that you may have already represented in a logical formula. There are a lot of knowledge bases such as DBpedia, Freebase, that contain a lot of domain knowledge that is already represented in a logical format. There's also, we haven't really started looking at this, but you can actually use a standard neural network to go from raw data to a logical formula that you can actually fit into a logical neural network. So you can have a hybrid approach where you have, standard neural networks working as future engineering, going from raw data to logical statements or representation that you can then fit into a neural network.
Thank you. That's a nice segue into my own question, so I'm just going to sneak it in. But I'm wondering if there's any overlap between these LNNs and your work in reinforcement learning, specifically in healthcare.
Currently, no, they are separate. But I am hoping that at some point, we can bridge the gap. So the requirement is that, so this requires that whatever domain or data we're working with can be represented in terms of objects and relations that exist in that domain. And I don't think all domains can be represented in that way. So at the moment, we're not doing that, but there's a team of researchers in the Tokyo lab looking at combining these LNNs with reinforcement learning on text-based games, where your state base is actually in natural language, so they have to do semantic parsing to go from natural language to logical representation, and they can actually use this logical neural networks in a reinforcement learning setting.
Super. Okay, our next question is from MN, who is asking about the publications that you mentioned right at the beginning of the talk. If it's possible to share the names again.
Or do I need to share my screen? I mean, they are on archive. I don't know if I can give you guys URLs to this.
Okay. Yeah, we can also.
Or do I need to share my screen
maybe
again?
maybe just share the screen again, then we can. If they're on archive, they'll be easy to find. I think that'll be the easiest.
Okay. Let me do that. Can you guys see them?
Yes. Thank you. Yeah, it'll be easy to refer to them if you come back to the screen and you go to the questions. The questions are listed in Crowdcast, so you can just hop to the timestamp where the question is answered, so it'll be easy to find. Thank you. Our next question is from Axel, who is asking if it is necessary to build a new LNN for each set of logical propositions that you would like to analyze.
Is it needed to build a new particular LNN? I mean, so I don't know if by LNN you mean a specific neuron, because in our case, an LNN is a network of neurons, and each neuron actually models a logical connective.
I think the question might relate to transfer learning, perhaps, if you can transfer between different logical neural networks.
So, well, I mean, if you're able to map your data into similar logical representations, I mean, you are able to transfer. So if I can give an example of, say, in reinforcement learning, when you learn to play a game. So in one task, you could be learning to stack objects on top of each other. So if the representation is, I have this object and this relation, so a relation can be on top, so one object is on top of another, it can be on the left, on the right. If you represent your domain in that way, these relations can be reused in a different task where you still need the relations and the same objects in the task. For example, now you're learning to, say, for example, in the kitchen, learning to wash dishes. So your robot is learning to wash dishes or something. You still need to be able to refer to the relations between the objects. You still need to put, say, a plate on top of a table. So all this information that you've learned previously can be easily transferred in a different task. So I don't know if that's what the question is asking.
Yeah, we can actually, if you don't mind, just indicating if your question was answered in the comments. Otherwise, we'll continue. Okay, while we wait, this did actually answer someone else's question. If about generalization. So I'm skipping to Cameron's question, which has already been answered with the generalization rules. But he's asking about regularization techniques and whether these can be harmful or not required. And if you could please give a comment on these.
Well, I'm not exactly sure. I've seen in applications where privacy is important, I've seen that regularization actually can harm performance, but can help with privacy. So they can be harmful depending on what you're most interested in. If all you want is performance, maybe, or performance in a specific task, then maybe you don't really need regularization. But if you want to be able to generalize, you probably need to regularize your parameters such that they don't overfit on the specific task that you're training on.
Okay, awesome. Then our last question, unless there is a bit of time left, if this is the last chance to sneak in questions. Our last question for the moment is from Tabang, who is asking about attempts at explainable AI. How far are we? And is our logic, I'm guessing human logic, the best bet?
So I'm not generally familiar with the whole work on explainable AI. So in our case, we're more interested in using background knowledge for sample efficiency and generalization. And it so happens that if you're fusing with symbolic AI, where you start with interpretable models. So these are rules that people have generated, so they actually understand, what's happening. This tends to lead to more interpretable models. I'm not sure if symbolic AI or logic is the ultimate way or our best bet. A lot of people do disagree with that. But there are cases where if you want to automatically learn rules from data, you could actually learn rules that make sense to the AI agent, but would require some work in analyzing the rules in order to be interpretable to the humans. But that is definitely better than what standard neural networks actually output at the moment, which is basically a bunch of weights, that don't really mean much. But there are other ways of trying to interpret these black box neural networks. Using attention models, so you can look at what the neural network was attending to in the input when making certain decisions.
Awesome, thank you. It seems we have a question. Another one, again from Axel. Okay, it seems we did not ask the question correctly. Sorry about that, Axel. So I'm going to ask it again. So he mentions that in the slides, logical neural networks are built based on the logical propositions where neurons are the connectors. So if the propositions are changed, is it necessary to change the neural network structure too?
Oh, okay. I see. Each connective, it is dependent on the propositions used at initialization. But if you have new propositions, you can simply add them to the network. There's no need to replace connectives that already exist. So you can have multiple conjunctions that work with different propositions. You can have multiple disjunctions, multiple implications that operate on different propositions. This is actually a graph where the only connections exist where propositions and connectives appear in the same formula, but you can have multiple formulas that are not related to each other within the same network.
Great. MN has asked, how does replacing KB ops, which we are assuming to mean knowledge-based operators, with their fuzzy equivalents affect the interpretability of logical neural network?
So there are actually neurosymbolic approaches that do replace this knowledge-based operators with their fuzzy equivalents and just use normal back propagation to update the neurons, and that actually it can actually change the behavior of the neurons. So they're no longer representing logical connectives. But in the LNN, we actually use constraint optimizations such that when you do backpropagation, you only update your parameters within constraints such that that specific neuron still behaves logically. So if it was a conjunction to begin with, you only update weights such that it still behaves like a conjunction. So in our case, it doesn't affect interpretability at all.
Okay, great. I think those are all the questions. I see Julianne might have disconnected for a minute, so we'll just wait for her before we do the closing. Otherwise, I will do the thank you.
Can you guys still hear me? I think my video feed may have just disappeared.
Yes. Oh, we can still hear you. Yeah,
Perfect.
sure.
Perfect. Okay.
But now we can see you, which is even better.
Oh, you can. Great. Let me just share my screen. Okay, let's see if this is working. Yep, there we go. Cool. So once again, thank you so much, Dr. Makondo. And let's everyone give him a virtual round of applause in the comments for this very great talk. And thank you to all of you for attending. Then also remember to subscribe to Nerve's calendar so you will be notified, or rather you will have access to our upcoming events. And Siobhan will share the link for the calendar in the comments just now. And then at the bottom of the screen today, you will see a button to a link for Nerve's designer. So do check out her page. You probably saw with the Avogadro Day, we have a variation on our logo and it's looking really, really cool. So definitely check out her work. Then lastly, also thank you to our sponsors, Stellenbosch University and Biomedical Engineering Research Group. And with that, we say thank you and good night to everyone.
All right, bye.
Bye.